So quite often in working with things, we're going to run into situations where we need to find the value of an integral, but we can't find an antiderivative. So a real famous one is this one, e to the negative x squared over 2 dx. It doesn't have an antiderivative yet. We're going to want to try and find the area underneath that curve between a couple points. Well, you're going to have to do something, and by analyzing the situation a little bit, if you try to break up your interval into little subintervals and then put in a trapezoid as an estimate of the area, you can come up with the trapezoid rule. Now, I'm not going to go through all the details of the trapezoid rule and how it's derived, but suffice it to say that for each of these little subintervals, you've got points. And you're going to evaluate the function at these points and put it together in such a way that you get a good estimate of the total area. So if you have n subintervals, t sub n is delta x, which is going to be the length of your interval divided by the number of subintervals, and then f of x sub 0, f of x sub n. These are your endpoints, so that's like your a and b, so f of a and f of b. Everything in between, you take and double it, and that's going to be your estimate of the area. So if you add more and more rectangles or more trapezoids, more and more points, subintervals, your estimate should improve. So let's take a look at that, and we'll do it with problem number 8. This is section 7.7. 8. So it's going to be the integral from 0 to 2 of 1 over 1 plus x to the 6th dx, and I want n equals 8 subintervals. So, wow, that's kind of a pain. That's a lot of little subintervals. It's a lot of work to do by hand, and I'm not really inclined to do a lot of work by hand. So we'll see if we can do something about that. Delta x is going to be the width of my interval, which is 2 minus 0 divided by 8, or 1/4. So the points that I'll be evaluating my function at are going to start at 0, and the next one will go up by 1/4, so it'll be 1/4. And then the next one will be what? 1/2, 3/4, 1, 5/4, 6/4, which is 3/2, 7/4, and then 2. So these are the points where I will evaluate my function. So the trapezoid rule would tell us that we got to plug things in this formula. And let's do that. The actual function that I'm going to be using is my integrand. That is my f of x. The trapezoid rule tells us I'm going to take delta x, which is 1/4, and divide it by 2. That's just the formula. And then I want f of 0 plus, and for a lot of the rest of this, I'm going to be taking 2 times the function. So 2 times f of 1/4 plus 2 times f of 1/2 plus 2 times f of 3/4. Yada, yada, yada. Getting kind of boring here. Plus, all the way down to the second to last one, 2 times f of 7/4 plus, and the last one doesn't get doubled, f of 2. Wow. So there's a couple ways that you can make your life a little simpler in terms of trying to find these values. Personally, if all I had was a calculator, here's what I would do. I'd start by plugging in the function y equals 1 over 1 plus x to the 6th, 1 divided by parentheses 1 plus x raised to the 6 parentheses. So there's my function. Hopefully you still have your table set up the way that we've used it all semester, and that is second, then window, table set. You should have independent set to ask. That way we can just find the values of the function that we need. So second, and then table, and we're going to need a lot of values. We're going to need f of 0, which is 1, not a big deal, and then f of 0.25, and then 0.5, 0.75, 1, 1.25, etc. Oops, go to 1.25, there we go, 1.5, 1.75, and 2. So you get all those values. Now, if you're not getting enough accuracy or digits in this column, then you can cursor over to that column and just go up and down to see as many digits as you need. So at 0.25, we got 0.9997, 5, which is around to 0.9998, etc. Boy, this looks like a lot of fun, huh? So 1/4 divided by 1/2 is 1/8. And now I got to put in things like 0.998998 plus 2 times, I'm only going to do maybe one more of these, 0.999846. You know what? Yeah, I'm sorry. So 1 plus 2 times that. Yeah, I was looking at the second one. All the way down to the last one, or just the second to last one, 2 times 0.0336 plus 0.0154. Yuck. That looks like a whole lot of fun. Let me see if I can't clean up that little part right here at the beginning. So it's going to be f of 0 is 1 plus 2 times f of 1/4, which is your 0.9998. Wow. All right. Well, certainly if I put this on an exam, I wouldn't choose n equal 8. I'd probably choose like 32 or 64. Just a minute. All right. No, I'd probably choose like 4 or something, something simpler. I also work it so that you have nice integer values to work with, so that it's a little bit easier. But let me show you one other possibility, and it's kind of a cool one. You can earn some extra credit if you learn it, and that is doing it on Google Sheets. I think Google Sheets is a wonderful way to do this. So I sent out you a link in that second email. So if you wanted to open that up, great. If not, that's fine too. Maybe you can just kind of catch along. So let's see. My first point is a 0, right? And the next points just keep on incrementing by 1/4, right? Well, I don't feel like typing all that in. Here's what I'm going to do. You can type in equals, and then click the cell above it. And what do we want to do? We want to add 0.25, right? Okay. But I need to repeat that. So this is kind of fun. You just drag the window down. Wow. That's cool. So that worked out pretty nice. Ooh, yeah, exactly. Now, well, that's what's cool about Google Sheets. I mean, if you learn Google Sheets, you're learning Excel. And I'll tell you what, 95% of employers are going to be really happy that you have some spreadsheet skills. So I'm more than happy to do that. In fact, when I teach stats, I use Google Sheets for a lot of it. But yeah, you get your certificate after this class. All right, so let's take for column B. Let me start this again. For column B, I'm going to click here, and you type equals 1 divided by parentheses 1 plus, I want to take this value, whatever it is, and raise it to the 6th power. So the raise is the up arrow key right above the 6. Raise it to the 6th power, and bam, I get 1. Okay. Now, I don't want to have to do that for all these, but the good news is I don't. Remember, see what trick's coming? You just drag it. Now you get all of those. Cool. Ooh, ah. All right, good. You catch it on. Now, I want this one. The end terms are just going to stay the same, right? So a 1 here, and let's just copy this one. So Control C or Command. Oops, how come it's not doing that? I just want to copy that, paste it. No, it's not doing what I want. Let's just do it this way. Equals this. There we go. But for the rest of these, what do I want to do for the rest of these? Rest of these, I want to double this amount, right? So equals 2, and then the times key is right above the 8, or you can get it on the keyboard on the right if you got one. Take that times 2. Now I've got all these values multiplied by 2. Bam. Cool. So that's the sum that I have in the brackets. So those numbers in brackets, that's what I've got right here. So I want to add those all up. And where's my sum? There's my sum. Sum of all of these. Boy, that feels a lot easier than doing this by hand. A lot easier. So let's take a look at where that puts us. I've got 1 over 8 times that total, 8.3260. So I want to take this and divide it by 8. So equals, and then click this cell, divide by 8, and that's the trapezoid estimate for the area underneath that curve. So about 1.0407, which is pretty good. 1.0407. Nice. Yeah. So, to keep everybody happy, we did this one by hand, right? All right. Good point. How are we looking on that one? Okay. So, the challenge for you is just coming up with these values. Personally, I kind of like doing it in a spreadsheet. It's kind of fun. Christian? It's not that it's non-differentiable. It's that it doesn't have an antiderivative. I mean, you could, with that one, 1 over 1 plus x to the 6th, there actually might be some ways to finagle that. You're certainly going to learn a lot more techniques in Calc 2. But if you can't find an antiderivative, a lot of times you still need to find the area. And at that point, you have to use some kind of numerical integration. And the trapezoid rule is just one of many choices. Okay. Let's see. Let me go look back here at this. So here's our trapezoid rule, and let me decrease the number of intervals just to make it a little bit easier to see. So that's pretty nice. The trapezoid rule is fitting a trapezoid between these points in each interval, and then it's finding the area underneath there. There's other possibilities. We saw some in section 5.1. You could use the right-hand endpoint and form rectangles. You could use the left-hand endpoint. You could use the midpoint. So those are all possibilities as well. And, they give you decent estimates of your integral. Now, there is one other possibility here in keeping things kind of simple, and that is instead of using, say, a trapezoid or the midpoint or something like that, what if I fit a little bit of a curve? What if I put in a quadratic equation there? Now let's stop and think for a second. between any 2 points, what can you draw? A line. You can always draw a line through 2 points. And the equation of that line is y equals mx plus b. But what if I added a 3rd point? Now what do I do? What would fit between 3 points? Yeah, and this isn't. All right, this is really terrible. I hate that this is on video. All right, but you can fit a curve. You can fit a parabola. Y equals ax squared plus bx plus c. And so what we're going to do is we're going to take 3 points in adjacent intervals, and we're going to fit a parabola. And when we do that, we get something called Simpsons Rule. So let's see, Simpsons Rule. Simpsons Rule is right here. So let me kind of move things around a little bit. Given it's kind of a funky little function, but yeah, right here. So with these 3 points, you fit a parabola. And underneath the curve, you're going to find the area of the parabola. And hopefully, that area is pretty close to the area underneath our original function. So that's what's going on with Simpsons Rule. It's much different in its approach, but the effect is pretty much the same in terms of the amount of work we're going to do. So let me show you the formula for Simpsons Rule. And that formula is right here. So it's going to be delta x, which again is going to be the width of your interval, divided by 3, which is different. The endpoints don't get multiplied by anything, but in between, we've got just a slightly different pattern. It's going to be 4 times x sub 1 plus 2 times f of x sub 2 plus 4 plus 2 plus etc. The pattern of the 4s and the 2s is going to continue across. So in terms of arithmetic, it's not a lot more work. It's no more work, really. It's just different, but yet you actually tend to get a much better estimate with Simpsons Rule than you do with the Trapezoid Rule. So let's try one with the Trapezoid Rule as well. In fact, we can try this current example. We can stick with that. So we're going to be evaluating at the same points. It's just that we're going to combine things a little bit differently. So Simpsons Rule. It's going to be delta x over 3. So delta x is again 1/4, this time over 3. And I'm going to want to take f of 0 plus 4 times f of 1/4 plus 2 times f of 1/2 plus 4 times f of 0.75 plus 2 times f of 1, and let me continue over here, plus 4 times f of 1.25 plus 2 times f of 1.5 plus 4 times f of 1.75 plus, what's the last one? F of 2. All right, so that's writing it out in almost all gory detail. I should just write that as 1/12, but f of 0 was 1. 4 times f of 1/4 is going to be 3.9990 plus 2 times f of 0.5. F of 0.5 was 0.98 something. 2 times that is going to be 1.9692. And I imagine that you're getting about as bored with this as I am. So let's kind of skip over here to the happy ending. At f of 2, we get 0.01538. And again, this is something that's nice to do by computer. I mean, with Google Sheets. So let me switch back over here to Google Sheets real quick. Let's see, Trapezoid Rule. I already did all that. The thing that's different about Simpsons Rule as opposed to the Trapezoid Rule is that you got to multiply every other one by 4 instead of all of them in between by 2. So you take this column times 4 to get this column times 2 to get this column, etc. If you add all this up in between here, you get 12.506065. So it's going to be 1/12 times 12.05, excuse me, 506065. Now 65. That's right. And 1/12 of that turns out to be 1.04212. So not too bad. The actual true estimate turns out to be 1.4099. So both of these are actually pretty close. How close a method is going to be is going to depend on how well behaved some of the derivatives are. But, you know, Simpsons Rule and the Trapezoid Rule aren't bad. Through Desmos. Yeah, to be honest. All right. Now, the nice thing about these rules and the advantage of these rules is you can use them in situations that where you don't have the function at all, where all you have is some values. So I think earlier I asked you to copy down some values here for problem number 32. You can apply Simpsons Rule or Trapezoid Rule to these types of situations where you're trying to find the area. In fact, I think it still might be up here someplace. Where do we had it earlier? The old final exam review. Final exam review. There we go. Oh, yeah, this won't work. So for your final exam review, one of the questions I put at the very end, I think, is a Simpsons Rule question. There we go. Which is to find the heartbeat of an athlete. How many times the heart beat during a certain interval of exercise. So you got this athlete that's exercising for 40 minutes. How often does his heart beat? Well, if you have the heart rate times time is going to tell you how often it beat. And if you have the heart rate here, you can find the area underneath this curve, which is how often the heart was beating, how often it beat during exercise. So we're going to do something similar with problem number 32. So we don't have any context for this one. We're just asked to use Simpsons Rule. So let me go back here and let's see, where did I put my data? There we go. So we're going to apply Simpsons Rule to this. And that'll give you the area underneath this curve as if we plotted it and used a nice continuous curve. Can anyone tell me what delta x is in this case? Yeah. So, or another way to look at it is, how far are you moving to get from one to the next? 0.2. Yeah, but you're right. 1.6 minus 0 divided by 8 is 0.2. So, or 1/5. So it's going to be 1/5 divided by 3 times Simpsons Rule divides by 3. It's okay. Trapezoid's a 2. f of 0 plus 4 times f of 0.2 plus 2 times f of 0.4 plus 4 times f of 0.6 plus 2 times f of 0.8 plus 4 times f of 1 plus 2 times f of 1.2 plus 4 times f of 1.4 plus f of 1.6. Now you don't have to write down this step. I'm just writing it down so you can see where all these variables are going to come from. Out in front, that's going to be 1/15. F of 0 is 12.1 plus 4 times 11.6 plus 2 times 11.3 plus 4 times 11.1. And I'm just getting these values from the table. Plus 2 times 11.7 plus 4 times 12.2 plus 2 times 12.6 plus 1.4 4 times 13 plus 13.2. Wow. Have fun with that. And I'll patiently wait for somebody to add that up for me. 1/15. I mean, I got it all written, but I just looking back at my notes, I didn't add it up myself. So I'll race you. Again, 288. 288.1. Uh-oh. Yeah, I'm wondering how we're going to, let's see, that would be a, all right, so 288, I'm going to leave a little room there in case there's a 0.1. I'm waiting for somebody to confirm that. 15. See what you're saying. 4 and 6 would be 0. 4. 288.1. I wonder where I'm off. 288.1. Okay. So 288.1 divided by 15. So 19.2. You know what? That's exactly what I did. Yeah. I left out the 0.1 in the first one. Yeah. So 6 bar. So about 19.21. Cool. So the nice thing about the Simpsons rule and the Trapezoid rule is that they apply in instances where you can't do other techniques of numeric integration. You have to do something else. Now, what you can appreciate is that we're making this a lot easier than it could be. A lot of times what follows work with Simpsons rule and Trapezoid rule is figuring out, well how bad could our estimate be? And the estimate can be off by this little error term. And this error term involves the fourth derivative and the length of the interval and this term right here, which is the number of intervals that you use. So, boy, getting a nice bound on this, trying to see how bad your error could be, is a lot of work sometimes. But if you're applying Simpsons rule to cubic polynomials, you should get an exact result. And you can see that because the fourth derivative of a cubic polynomial would be 0. So Simpsons rule is going to be exact for those things. Trapezoid rule, likewise, has its error estimates. You see the Trapezoid rule is not quite as good as Simpsons Rule because its bound isn't divided by as big of a number, and its bound is going to depend only on the second derivative. So, which, actually that might not be a big deal, but the term here in the denominator is bigger for Simpsons Rule. Cool. Well, enjoy working with Simpsons Rule and the Trapezoid Rule.